Hey everyone! So today, Monday, we're going to go over intermolecular forces, which is what you did the Google Doc on Wednesday and Thursday. Some of you might not need to watch this video. Maybe you understood everything through the Google Doc, but in case you're confused, hopefully the PowerPoint today clears everything up. Okay, so intermolecular forces are attractive forces between neighboring particles. So not inside a particle, but between particles. For example, here's a water, here's a water. There are forces between the water particles. We've always talked about ionic and covalent bonds, which are inside the water, but intermolecular forces are between particles. In a polar molecule, just reviewing, one end of the molecule has a slightly positive charge and the other end has a slightly negative charge. Any molecule that's got a positive end on one side and negative end on one side that's asymmetrical is polar. And you'll often see the word, it says it has a dipole. That just means it has charges, a positive end and a negative end. That's all a dipole is. When you hear dipole, just think polar molecule. Don't think anything weird with that. And so I just went over this. The intermolecular force is between molecules, and intramolecular forces are inside molecules. So ionic bonds, covalent bonds are both intramolecular forces. Intermolecular forces are the new stuff. Okay, this picture was on your Google Doc. And so our intramolecular forces were, I know it's kind of blurry, inside connecting the oxygen to the hydrogen, while the intermolecular forces were between them. So just hitting on that point again. And so our types of IMFs. Moving on. The first type is London dispersion forces. These happen between nonpolar molecules. They also happen between polar molecules, but between polar molecules, they're not the only thing there. And so what happens is with London dispersion or van der Waals forces, they're called both names, there's a temporary charge that exists when the nucleus of one atom attracts electrons from a neighboring atom. So pretty much two atoms get near each other and they attract each other. It is a very short-lived attraction and it's the weakest kind. And this again happens between nonpolar molecules, but polar as well. Polar molecules also have this. And again, it's just two atoms get together. The nucleus of one attracts the electrons from another, and they just get a short-lived attraction. Dipole-dipole bonding occurs between two polar molecules, and they're attracted to each other because there's a partial positive end and a partial negative end. Opposites attract. And so down here I have two pictures for you. One you already saw, two HCl molecules. They both are polar molecules, and the chlorine is the partial negative, the hydrogen is the partial positive, and you can see there's an attraction between the positive and the negative end of them. And then on the right side, this molecule right here, we've got, what do we have over here? Oh, we've got water and HCl. Oops, I should have noticed that earlier. And the water, the oxygen is the partial negative. The hydrogens are the partial positive. And then in the HCl, the hydrogen's partially positive, the chlorine's partially negative. And you can see there's an attraction between the H of the HCl and the oxygen of the water because the positive and the negative attract. And then on the other side, there's an intermolecular force between the H and the water and the Cl because positive and negative. So dipole interactions occur between two polar molecules. If it's not polar, it doesn't have this force. And this is a relatively strong force. Here's another picture. This was on your Google Doc, and I believe I asked you what end would be attracted to what. And so this already has the positives labeled and the negatives labeled. And I'm going to use red. The hydrogen from HI would be attracted to the iodine of another group. This iodine would be attracted to that H. This H would be attracted to that I. So there would be forces holding all of these together. And that would be dipole-dipole forces. There's also van der Waals forces occurring, but van der Waals forces again are very weak, and so they don't play a major role in polar molecules. And then hydrogen bonding is when you've got hydrogen, as the name says, and there's a very polar bond. And this is the strongest type of intermolecular force. And so what do I mean by a very polar bond? You need to have H and N bonded together, H and O, or H and F. If you don't have one of those three bonds in a molecule, there's no hydrogen bonding. And it should say on here, your molecule should also be polar, which if it has any of those, it's a polar molecule. And so hydrogen bonding is just an extremely strong dipole-dipole force. And you can see it in the little drawing below. This is a water molecule, water, water. And it's really just like what I drew before. It's just this bond is stronger than dipole-dipole forces. So this would be stronger than the HI force that I drew on a slide back because this H is connected to the O. Now, if that hydrogen, just like before, if it was an HI, that is not hydrogen bonding because it's not one of those three listed. Those three are the only three bonds that can have hydrogen bonding. Nothing else can. Not HI, not HCl, not H2S, nothing. Just those three. And then here, to watch the little GIF. Okay. And here is another diagram. This is NH3 ammonia, not the polyatomic ion, ammonium. This is a polar molecule. The nitrogen has partially negative. Your hydrogens are partially positive. And because there's an H bonded to an N, it has hydrogen bonding. And so you can see that there is an attractive force between the negative nitrogen here and the positive hydrogen of another molecule. And then this one over here would also have an intermolecular force. This H would be attracted to the N of that molecule. And then they would be attracted as well. Those would all be hydrogen bonds. And this picture was in your Google Doc. Not the left side, this wasn't, but the right side was about the krypton atom. And so this showed dispersion forces or van der Waals forces. And so what's going on here, we have a krypton atom, it's neutral, and then in part D, you can see all of the electrons are kind of over here for a brief second. And when they're over here, this side becomes partially negative, this side becomes partially positive, but this just happens for a second, and it happens when there's another atom nearby on either side. And there would just be a little force between them. But because this is dispersion forces, this is the weakest IMF, and these, should say M, not N, and these electrons would not stay over here in part D for very long. They would eventually go back to here where they're all pretty much spread out and there's no partial charge. So again, just reviewing dispersion forces, this is the weakest IMF. It happens between all molecules, but it's the only IMF for nonpolar molecules. And it's just they get a temporary charge when there's another atom nearby. Now, the strength of intermolecular forces, it depends on the properties of the substance. There are some dipole-dipole forces that are stronger than other dipole-dipole forces. And generally, the more polar a molecule is, the stronger the IMFs or the dipole-dipole forces are between them. So something that barely is polar is not going to have a very strong dipole-dipole force compared to something like water that is extremely polar, that has a much stronger intermolecular force between them. And so why does this matter? Phase changes. If I want to melt something, vaporize, boil, sublimate it, you have to break intermolecular forces. And the amount of energy you have to put in depends on how strong the forces are between them. If I want to break apart water molecules, my water, they have a really strong force between them. That's going to require a lot of energy to pull them apart. And if I want to boil something or go from a liquid to a gas, I have to break those intermolecular forces. And so it requires a lot of energy versus something that doesn't have very strong intermolecular forces. It's easier to break them. And then if you wanted to freeze something, condense it, deposition. Now all of those, freezing, liquid to solid, condensation, gas to liquid, you have to form intermolecular forces. And they, when you actually do these phase changes, they release energy as the particles move to that lower energy, or they just move to the other state of matter. Do not worry about that lower energy conformation thing. They just, as they move to those states of matter, they release energy. Okay, so we're going to do some practice problems really fast. Dipole-dipole, London dispersion, hydrogen bonding are intermolecular forces. True or false? True. Those are our three intermolecular forces. Intermolecular forces, next one. Describe the attractive forces between one molecule and another molecule. True or false? True. Intramolecular forces describe the bonds between atoms within a molecule. True or false? True. Covalent, ionic, and metallic bonding are the three intramolecular forces. True or false? True. And hydrogen bonds are the strongest of the three intermolecular forces. True or false? Also true. And that is all for today.